Hi, statistical students. I want to go over hypothesis testing before our test on Monday. Here's an example from the book. Is the average human body temperature really 98.6 degrees? When it was measured, were the thermometers accurate? Have people really changed their body temperatures? Alan Shoemaker did a study on trying to come up with what the normal temperature temperature and heart rate were for different people. This was a study published in 1996. We actually have the data under body temp, and it will be in stat key as well, just the body temperatures, not the pulse rate or the gender. Looking at, we can see the box plot, dot plot of the data shows that it's approximately normal, and a size of 50 with a mean of 98.26 and a standard deviation of 0.765. Does this data provide significant evidence that the average body temperature is really different from what is said? Let's go to stat key. I get that. Okay, so let's just go ahead and do randomized hypothesis test since we already have the data. And sure enough, here's body temperature. If we look at show the data table, we'll see all these temperatures right here, starting with 97.6. Here's the dot plot for our temperatures. And if we use the bootstrap to generate 1,000 samples, we can see, approximately the mean of all these samples is approximately normal. We're interested in differences, so that's going to be a two-tailed difference. We can just put in the number that we actually get is 98.26 because, considering if the null hypothesis was true, how likely are we to get this result? Well, it's going to happen about 1/10% of the time, although we have to double it and make it 0.2% because it's two-tailed. I'm showing you here a screen I captured earlier because I want you to see what I concluded right here. The data provide significant evidence at the 5% level, because we're chopping it off at 5%, that the average body temperature is really different from the standard that's already listed. But what if we don't have the data? This is where our theoretical distributions come in. So in Chapter 6, we get told we have a sample of 50 healthy subjects, a mean body temperature of 98.26, and a standard deviation of 0.765, and asked to test whether there is evidence that the mean body temperature is different from 98.26. Okay, can we do a hypothesis test? Well, we don't have the original data, but we do have a reasonably large sample, and the data looks approximately normal. So sure, let's do a hypothesis test. We set it up with a null and alternative hypothesis. Now, if you have to type it out, you can do H0 or HA instead of the null and alternative written this way, and mu written this way instead of the Greek letter, and this symbol for not equals. I prefer you either handwrite it or use a formula or equation writer, but whichever works for you, I will be happy with. Step 2, we need to be able to test it. For example, if you have a 90% significance label, then we say we're going to test against alpha equals 10. This is our rejection region. We're going to say everything that is less than 10% we reject. If it's greater than 10%, well, that's in our 90% significance level, and we will fail to reject. If there's nothing stated, go ahead and use alpha 0.05. Okay, we need to decide what we're going to do. Since this was from a large sample and we're testing a mean, we're going to just use the t-distribution with 49 degrees of freedom. Remember, your sample size was 50. So we need to find the standard error, which is going to be the sample standard deviation divided by the square root of the sample size. In this case, our answer is going to be 0.1082. I went out one extra decimal from the numbers I was given just for calculation purposes. We're going to round back when we get to the final answer. Our t-value is found by the value we get from the sample, subtract by the value that's stated in the null hypothesis, divided by the standard error, which gives us negative 3.142, which means we are at more than 3 standard deviations below the mean. That's pretty extreme. Well, I'm going to go back to stat key and see what I can do there. Okay, I'm going to go to the index and come down to the theoretical distribution of t. I have 49 degrees of freedom, and I am testing right here of how extreme that value of negative 3.142 is. So I put in a two-tail from the alternative, type in that negative 3.142. I've got an extra 0 in there, sorry. There we go. Hit OK. And here's our probability. Not very big. Okay, now remember, you've got to double the probability. So that gives us a pretty small p-value. That's about 0.3%, which is really close to the method the numbers we found with using the bootstrap method. So we need to say the result. Either we're going to reject the null hypothesis or fail to reject it, because our results are inconclusive. Since our p-value is less than our alpha, we feel confident that we can reject the null hypothesis. And then we need to make a conclusion about what this means. So just go ahead and take the original statement, test whether there is evidence, and then go ahead and restate it. Say there is evidence at the 95% significance level. See, notice how I put in my significance level here. Even they didn't state it in the original one, so I put it in that this is where I tested, to conclude that the mean body temperature is different. Okay, your final document should have all these pieces in here. So you'll be given a statement right here. So here's your sample size, your mean, your standard deviation, and told to test. So you put in null and alternative hypothesis, a cutoff point, standard error, a test statistic, your p-value. Comparing your p-value to your alpha lets you decide whether to reject or fail to reject your null hypothesis, and then you state your conclusion in terms of the original problem. That is a hypothesis test, and this is your instructor, Christine Chipman, signing off.